Good evening, class. I am Mohit, and this is a TA class number 7, and I'll be discussing. So, it's a class which is based on the quantum Hall effect. It is a course offered by NPTEL 2025, and today's class, this is like assignment number 6, class 7. Yeah. So in this coursework, as from the name you can see, it's a quantum Hall effect. So we are discussing origin of the classical Hall effect, and then moving towards the quantum Hall effect, and then afterwards the effects on the spins and what you call the Raspa spin orbit coupling, Ken-Melle spin orbit coupling. All those things we'll be discussing. So, what are the learning objective of this class? This class. First, you will be able to write continuity equation for spin resolved densities and current. So write continuity equation for spin resolved densities and current. Then derive Raspa Hamiltonian for 2D electron. Afterward, then we'll solve for the eigenvalues and the eigenstates for these helical spinors. Then we'll be computing the spin resolved density of states. And then I'll be discussing the Hamiltonian, which includes the perpendicular magnetic field and the G-man terms. Yeah. So these things will be covered mostly in this lecture. Now, starting with the very beginning, and with the first question, which goes like, write down the continuity equation for spin current J sigma, where sigma is the spin notation, up or down it can be. So this is the question which I phrased, that write down the continuity equation for the spin current. Okay, so let's set up notations first, right? So set up and notations. Let's assume psi be the wave function, psi r, which is a function of position and the time, rt, and there are two spinors, which is up spin and then the down spin, psi component of a spin and down spin. So it's a two component spinor. Yeah. So we define a spin resolved particle density spin resolved particle density, which we call n sigma, position of function of position and momentum, and given as modulus of psi sigma rt square. And similarly, we define also the spin resolved probability currents. Similarly, spin resolved probability currents So this is the same structure as the usual Sondiger current, but acting on each spin component essentially. So whatever I'll be writing will be with no electromagnetic field. So J sigma will be H bar by 2 mi iota, and then complex conjugate of psi sigma star, gradient of psi sigma, minus gradient of psi sigma star psi sigma. So this is in no electromagnetic field, no EM field, right? And if a vector potential A is present, then in case if vector potential A is present, then we know that P goes as P minus EA, right? So similarly here the gradient will go to gradient minus I E by H bar times the uh, vector potential A. This is the standard way, right? Now continuity with possible spin flips, right? In the absence of any spin mixing terms, each component obeys uh, this continuity equation. Okay, so continuity with possible spin flips are allowing the spins to be flipped because the charge numbers is same, our charge carrier is same, but the spins are not conserved. That's what essentially it means with possible spin flips. So in the absence of any spin mixing terms, each component obeys gradient of J sigma to 0. With the spin orbit coupling or other spin flip process. So probability is exchanged between either upspin to the downspin or downspin to the upspin. So a convenient phenomenological form will be, let me write whatever I'm saying. So with spin orbit coupling or other spin flip process, probability is exchanged between spin up and spin down. So a convenient phenomenological form will be, you write it for individual spins and their conversion. So del T and up plus gradient of current density of upspin will be equals to, there will be a term which will be converting from down to up, so that will add up, and there will be a term which will be converting from up to down, that will subtract. So minus gamma plus, so this is the term, minus term where up is converting into the down, plus there will be a term where the down spin will be converting to the up, right? So this is equation number 1. Similarly, gamma t and down plus gradient of J sigma down will be minus of conversion from down to up plus up to down. So what do you see from equation number 1 and 2? That the right hand side can be non-zero for both of them, right? But if you add 1 and 2, so the total, so the what equation number 1 and 2 tells you is that the spins, number of spin is not conserved in the system, right? But the total density, which will be number of carriers of spin up and the spin down, will still satisfy the charge neutrality condition, the charge continuity condition basically. So this essentially mean the total density which you call n is equals to n up plus n down, so still satisfies the charge continuity. What do I mean by this? So what I mean is, like, if you take n plus gradient of upspin plus j down is current density of downspin, this will be equal to 0, right? And with if you just write J is equals to J up plus J down, this is essentially the usual particle current. Right? So essentially your equation boils down to the continuity equation of gradient of J equals to 0. So what it tells you, equation number 1, 2, tells you that the spin number is not conserved. Since the right hand side can be non-zero. But from equation 3, you know that the particle number, the number of the charge carriers are conserved. So that's what this continuity equation is all about. So a question which was write down the continuity equation for spin current J sigma, sigma equal to up and down. This is equation number 1 and 2. And equation number 3, you show that okay, the spins can be interchangeable, but the number of the charge carrier is constant. A system, closed system. Yeah. Now, let me phrase another question for you, which will be that write down the Raspa spin orbit coupling term, and then assuming a parabolic dispersion, write down the Hamiltonian including the Raspa term, and then solve for the dispersion, like how the dispersion will depend on the Raspa term. So that's the question. So question is write down the Raspa spin orbit coupling term, then this is the first part. The second part of this question will be assuming a parabolic dispersion in two dimension, write down the Hamiltonian including the Rashba term and solve for dispersion, energy dispersion. So this is the question. Now we'll have to address this one. So so first let's discuss the Rashba term standard form. Yeah. So the Rashba spin orbit coupling, why it's called spin orbit coupling? Because it couples the spin and angular momentum. That's why spin orbit coupling, SOC. which arises from structural inversion asymmetry in the z direction. So whenever there is a structural inversion symmetry in the z direction, then it arises. So in arising from structural inversion asymmetry in the z direction, it's the Hamiltonian part of it is written as HR. You can write Hamiltonian for Raspa. Alpha is the Rashba parameter times sigma x py minus sigma y px. So you can already think that sigma cross p, it's essentially that's why. And where alpha is Rashba parameter and p is the momentum operator, and where pi I can write it to be minus I h bar del by del I, so I will write it del I, and sigma xy are the Pauli matrices. Zero one one zero one zero zero minus 1, the Pauli matrix, you know. And then this is about the Hamiltonian. Now the second part of it, it says that assume a parabolic dispersion in two dimensions and write down the Hamiltonian including the Raspa term and solve for energy dispersion. Okay, this one we'll do now. So full energy full single electron 2D Hamiltonian with parabolic kinetic energy. No magnetic field. So in momentum representation, P will be what? H bar K. And for that one, you can write your uh, Hamiltonian Hk as h bar square k square by 2m plus this hr term which you have written uh, on the top, which will be alpha times yeah, which will be alpha times h bar Planck constant, and then sigma x ky, because you have replaced your momentum p to be the h bar k, so the h bar has come out, and minus sigma y kx. So this will be your equation number 1. This will be equation number 2. Now here you can write in, in this part you have used k, where k is essentially square root of kx square plus k y square. And the first term which you are seeing, this is the first term. It's the usual 2D free electron kinetic energy. And the second term is the Raspa term. So let me just mark it. Usual 2D free electron kinetic energy. and this one is the Rashba term. Okay. Now comes the point where we'll have to find the eigenstates. So finding eigenstates. Yeah. So we will write the spin orbit couple term as a 2 by 2 matrix in the spin basis using k equal to square root of kx square plus ky square, and the polar angle phi, which will be arctan to ky kx. So essentially we will write the spin orbit couple term as a 2 by 2 matrix. So you write your alpha h bar to a sigma x ky minus sigma y kx to be alpha h bar k 0 iota e to the power minus I phi minus iota e to the power minus I phi. Here this will be complex conjugate, so this will be plus 0. So the eigenvalues of here also you can write it to be I identity matrix 2 by 2. So the eigenvalues of hk then are therefore, so you can compute the eigenvalues, and you can write the eigenvalues to be plus minus k to be h bar square k square by 2m plus minus alpha h bar k. So the two branches E plus and E minus are the Rashba spin split parabolas. So the lower branch which will be E minus attains its minimum value at some different k, and similarly the for E plus the minimum value will be at different k, right? And the splitting between the different branches at fixed k is also fixed. That will be the difference between E plus and E minus. That will always turn out to be 2 alpha h bar k. So if I have to make comments on it, then the two branches. So okay, if you have to draw the E versus K, right? First I will draw for alpha equal to 0. So it's a parabola with alpha equal to 0. Right? Now we'll have to draw for a positive alpha, right? For so they will be what? They will be shifted in K's essentially. So one will be shifted left, other will be shifted right. Right? And it can be lower than 0 also. So its minimum value will come around at k equal to 0. This will be having a value 0, and then it will be having this one, and change its color. And for plus, it will be somewhere like this. Yeah, so this red one alpha equal to 0, blue one is alpha is equals to positive and E plus. E minus. This green will be alpha equals to positive, E plus. So you see that for the alpha equal to 0 dispersion gets broken into two part, which are specially separated with respect to each other, and the what you call essentially your energy band dispersion are shifted in your, if this is your x kx, so they will be shifted in k in respectively k, right? E versus k. So they are split like, and this structure which gets formed here, this between these two bands, it's like a Mexican hat. It goes like this, right? So it's like a Mexican hat kind of structure, and this kind of thing leads to the band inversion also, and then a helical edges, all those things show up. So if I have to make the comments on it, this one. So the comments, yeah. So the first comment is that the two branches, that is E plus and E minus, are the Raspa spin split parabolas. The two branches E plus and E minus are the Raspa spin split parabolas. That's the first comment. You have to make the second comment. So you see that the two branches E plus and E minus, they attain its minimum value. So the lower branch, let me call it the E minus. So the lower branch E minus attains its minimum at k is equals to k rashba, let me call, and that will be equals to m alpha by h bar, and with minimum energy E minimum is equals to minus m alpha square by 2. Whereas the splitting between the two branches is fixed. The splitting between the two branches is fixed. So delta E, that will be E plus minus of E minus will be 2 alpha H bar K. So these are the comments on this transfer spin orbit coupling thing. Yeah. If you have any question or doubt till the point, you can ask me here. I'll be happy to address your concerns or your points. So till now I have discussed two questions. First is regarding the continuity equation for spin back currents basically, and in the second question I have discussed the Rasbach spin orbit coupling term. Yeah. If you don't have any question, then I will move on to the third question essentially, which will be in the question number 2 we have solved the energy eigenvalues. Then I'll be asking, phrasing a question, what will be the wave function corresponding to this Hamiltonian, which is equation number 2. So what will be the wave functions corresponding to the Hamiltonian, and I'll be discussing those wave functions. So yeah. Question number 3, which says that okay, what are the wave functions corresponding to Hamiltonian in equation 2? So we'll find the eigenvectors of these spinors for the two branches. So we have seen that there are two branches, E plus and E minus. So we'll be solving the equation for that only, right? And we'll be getting the normalized eigenvectors, which will be a combination of plane wave times the spinor, right? So we find the eigenvectors. Just a minute, I'll have to check the power. Depot. We find the eigenvectors as minus for the two branches. So we'll be solving h of k minus e of plus minus k plus minus for the two states basically, and then wave function chi plus minus equals to 0. So from the matrix form, the normalized eigenvector will be a combination of plane wave and a spinor, and we can write, okay, let me write from the matrix form discussed in question above. The normalized eigenvector which will be plane wave times spinor uh, psi k plus minus r equals to 1 by square root of a e to the power ikr plus minus 5. And there chi plus minus instead of 5 is 1 by square root of 2 1, then minus iota plus minus 4 plus minus 8 and e to the power iota 5. Or I can write it more compact also. More compact form chi s 5 will be 1 by square root of 2 1 is iota s e to the power I5 with s equals to plus 1 for upper branch and s equals to minus 1 for lower branch. Right? So now the explanation of it goes as so the full eigenstate is a plane wave e to the power I kr, that is the plane wave part, by square root a. Square root a is the normalizing factors times a two component spinel, which we write here. This equation number 1. So equation 1 is a so let me write full eigenstate is a plane wave e to the power ikr by square root of a, where this is the normalizing factor. Times a two component spinel equation number 2. Equation number 1, sorry, equation number 1 here. Yeah. And the spinner shows the characteristic of spin momentum lock-in. So the spin is lying in the plane perpendicular to k for the Rashba, because you see for the Rashba term in the Hamiltonian, as you can see, your it's sigma x k y kx. So they are like the cross product cross k, sigma cross p, or essentially you can say the spin and momentum are low, and that's what it is. So the spinner shows the characteristic spin momentum lock-in so the spin lies in the plane which will be perpendicular to K. This is for the Rashba, and its azimuthal dependence is encoded by e to the power I phi. Yeah. If one you want to verify, they can also verify if they operate HK on the psi s, it will give you the ES where S can be plus and minus times the psi S where psi is your wave function. Yeah. So that can also be verified. Now we have written the wave function corresponding to the Rashba two-dimensional electron gas in zero magnetic field. Now the question comes that write down the expression for the spin resolved density of state. How will be the spin resolved density of state will be for the Rashba term in a two-dimensional electron gas. So the next question which I phrase is okay. Write down the expression for spin resolved density of state G sigma is for spin up and spin down, up and down. For Rashba term with parabolic parabolic dispersion to deck. Yeah, that's the question. Now, our goal is to compute the density of states per unit area resolved into spin either up or down. And there will be quantization alongside. So, I'll just write. One second. Yeah. Yep. So, our goal is to compute the density of states that will be per unit area and will be resolved into spin state. Right? So, I'll write the general expression. So, this is the projected density of state basically. So, the spin resolved density of state for spin up and spin down let me write sigma which belongs to either up or down, either one of them is G sigma E. E is for the energy and 1 by 2 pi square some summation over all type of spins plus and minus and then del 2k spin part sigma chi s wave function sigma, and then this will be a function of azimuthal angle. This will be multiplied with delta E minus ESK. So this S is stands for the two bands, which we saw in the Rashba term, that the band dispersion gets splitted. And because the Rashba eigenspinors above satisfies this will be independent of so the projection on the sigma equals to z basis is simply half. Thus half G total. And so this is if the spin numbers are equal, right? It's not a ferromagnet kind of thing. Then the number of the density of upspin and density of downspin will be independent of the phi azimuthal angle, and the projection of the spin will be half of the total density of state. So here G total of is equals to total both spin density of state. Now we can compute the G total also, that what will the G total be. So now I'll focus on that. So this will be computing G total is a function of energy. So we'll start with the standard K space integral, starting with standard K space integral. So your G total is a function of energy E, will be 1 by 2 pi square integral over T to K. S is equals to plus minus, that is the two bands, and then summation over energy K for both the bands. And if you do so, it will be equivalent to essentially 1 by 2 pi d2k. You can write 2 pi k dk, so that will also go in. So s is equals to plus minus 1 2 pi goes away, and then there is summation over k. See, the integral you convert to the summation, and then ks by del es by del k at k is equals to ks. And for the branch S, the dispersion is, we know, so if I have to write ES K, we know that it was h bar square k square by 2m plus S. So here S can take value plus and minus, right? So there are two bands, you know, alpha h bar k. Now solving for k at fixed epsilon will give the uh, single positive square root, right? So we write by solving for k at a fixed energy. At a fixed energy, if you solve it, what you will get will be ks kr square plus 2m epsilon by h bar square, where kr is essentially m alpha by h bar. We can compute its derivative also. So if it's here to compute the derivative del es by del k, then in that case it will be h bar square k by m, and then plus s alpha h bar. You can take here h bar square by m to be the common, and that will give you k plus skr essentially, right? And if you do some algebra, so this is equation number, okay, for this question, let me call this is your equation number 1, this is your equation number 2, this is equation number 3, and this is equation number 4. If you combine equation number 1, 3 and 4, if we combine these ones, what you will get will be G total, which you are computing here in equation number 1. This is 1 by 2 pi summation over whole s and summation over ks by del e by del k. What you will get will be G total will be m by pi h bar square for energies where both branches exist. Yeah. So for energies E greater than 0, both branches contribute and the total density state is constant, right? Energy independent and equals the usual 2D electron free electron gas density state, which is m by pi h bar square, right? And therefore For up spin, it will be half of it. Up down spin, it will be half of it. Right? For energy is greater than 0. That's what you have seen. And so for energies above 0, the Raspa splitting redistributes states between the two branches but does not change the total density of state. So let me write the physical remark of it. Yeah. For energies ln greater than 0, both branches contributes and the total density of state is constant. That means energy independent and equals to the usual two-dimensional electron gas density of state, which is G total is equals to m by pi h bar square for E greater than 0, and therefore G up equal to G down is equals to m by 2 pi h square. This is for E is greater than 0. Like, but for the energies which are there in the window minus m alpha square by 2 to 0, only the lower branch has states, right, in that range. So the density of state is given by the single branch formula. Okay, so let me write. One second. Oh, this is true for every time, I think, because let me just remove this part because for all the cases, so the both branches will contribute anyway full time. In the case of the RAS batteries, they will contribute. Yeah. So this is over. Now, moving on to the next question, which I will phrase to be that write down a Hamiltonian for a single electron in a two dimension in the presence of both the uniform magnetic field in the giant direction and the Raspe spin-orbit coupling. So now, along with the Raspe spin-orbit coupling, I'll be introducing the magnetic field which will be pointing in the z direction. Right? So, and we have to write a Hamiltonian for the same. So, write down a Hamiltonian single electron in 2D XY plane in presence of both a uniform magnetic field in the z direction and Rashba spin-orbit coupling. So, minimal coupling will be when you put spins into the presence of the magnetic field. What happens? The spin gets coupled with the magnetic field, and that's like the minimal coupling is the Zeeman term, where your like half g mu b and the magnetic field times your spin, right? Spin quantum number. So that's what will also get included in your Hamiltonian. So if I have to write like the Hamiltonian, so for the first term will be what? H bar square k square by 2m, right? Along with that, the second term will be alpha times the spin and the momentum, which are like cross with each other, and then the third term, which will be the Zeeman term. So if I ask you the Hamiltonian, so also for minimal coupling Hamiltonian, which includes Zeeman term. So for an electron, charge minus E is greater than 0, right? And which is in magnetic field B equal to Bz cap. Then we'll use the kinetic momentum, which is pi will be pi plus Ea, right? So the kinetic moment will be the canonical momentum plus the vector potential part. So the kinetic momentum will be essentially pi, so the canonical part P plus Ea. So the 2D Hamiltonian, therefore, the 2D Hamiltonian will be having three parts. So H will be having of H kinetic plus H Rashba plus H Zeeman. So if I were to write it, what I will write, H will be pi square by 2m, that's the kinetic, plus alpha times sigma x pi y minus sigma y pi z, that's the Rashba, and finally the Zeeman, which will be half g mu b. Mu b is the Bohr magneton, and b times sigma z, and g is the Lendegee factor. So here let me just explaining the notations. The first is pi, which is pi x, pi y. You write as p plus ea. Here p is px plus px and py. Right? Is the this is gauge invariant, gauge covariant. It's not gauge invariant. It's gauge covariant. Kinetic momentum operator. Yeah. A is the vector potential which satisfy curl of A. A is vector potential which satisfy curl of A is equals to B. Okay. This is the common case. Alpha we have already discussed. It's a Rashba strength term or Rashba coupling term. Right? G is the Lambda G factor and mu B is the Bohr magneton. Generally G is half and mu B is Bohr magneton. So this is the minimally coupled. If you take minimal coupling with the magnetic field with the spin part, or if you don't want to take this Gman term, then also the magnetic field results are included in as a function in the kinetic momentum operator, which has the canonical momentum part plus the vector potential part, which take care of this magnetic field in the Hamiltonian. Now this is over, but I can put forth more such questions which are like just tiny subsections of what I have discussed. So this question 6, which I will pose, that show that the expectation value of spin is always perpendicular to the momentum in Raspa band. To the momentum. Raspa band. शर्म कर करवा लिया है चूतिया. So chi s phi will be 1 by square root 2 1 minus is e to the power I phi, and we can compute its expectation values. This is the wave function which we have derived. We can compute the expectation values. With the Pauli matrices sigma x, sigma y, sigma z that you all know. The Pauli matrices, how you compute the if for example if you have to compute the expectation of sigma is, how will you do it? You will take this wave function is stagger, yes sigma I, and chi s. Yeah, that's the and these are the Pauli matrices. So if you compute it, so after algebra, so let me write the Pauli matrices for you. It is 0 1 1 0. Sigma y is 0 minus iota iota 0. Sigma z is 1 0 0 minus 1, I think, if I remember it right. Yeah. So sigma x is 0 1 1 0, sigma y is 0 minus iota iota 0, sigma z is 1 0 0 minus 1. If you use these ones and the Hamiltonian, the wave function which is written on the top, then what you will find will be that the expectation value of sigma x is essentially s times sine phi. Sigma y will be s times minus s times cos phi, and expectation of sigma z will be essentially 0. So the spin expectation vector, if you have to write, so the spin expectation vector equal to s times minus z cap times k cap, meaning that the spin lies in plane and is always perpendicular to the momentum. Implying spin lies in plane and is always perpendicular to momentum. Yeah. Then we have already found, if I ask you, okay, what will be your what you call the Fermi wave vector corresponding to the two Rashba bands at a fixed energy, then this will be your answer. Ks at a fixed energy E, your uh, Fermi wave vector K will be S can be taken value plus and minus depending on E plus and E minus band. So minus skr plus square root of kr square plus 2m epsilon by h bar square. So that these values will be the Fermi wave vector value, and that's it. So in today's class, if I summarize, we have discussed the continuity equation for spin result densities and current, and what we have shown is that the spins are not conserved, but the total number of the charge carrier is conserved. That's one thing which we have shown here. Then we derived the Rashba Hamiltonian for 2D electron, right? We solved its eigenvalues and eigenstates with the helical spinors basically, and we showed that okay, we also computed the spin resolved density of states and showed that for a non-ferromagnetic system, both the spins have equal weightage and they are half of individual strength is half of the m by pi h bar square. That's the class. That's the standard two deck density state. If you combine both spin and down, spin up and spin down, you get the full two deck states that is independent of the carried energies basically. Then we also looked at the Hamiltonian, which includes the perpendicular magnetic field, that's the Zeeman term, and the Rashba term also, and how your canonical your momentum transfers from gets a function of a canonical momentum and vector potential A. That's also we discussed. Then we discussed about that the spin in the Rashba term spin lies in plane and is always perpendicular to the momentum. So these are the points which we have discussed in today's class. So if you have any question or doubt, you can ask me in the class. I will be happy to address your concerns. Uh, I'll wait here for 5 more minutes. If you have any question or doubt, you can discuss it in the comment section. I'll be happy to address your concerns.